Introduction to Gravitation. The planets in our solar system, including the Earth, move around the Sun in a regular pattern. The Earth revolves around the Sun in a stable orbit because of the gravitational force of attraction between the Earth and the Sun. To understand the stability of our solar system, we must learn about the gravitational force of attraction between the various celestial bodies present in the solar system. In this lesson, you will be able to state and use Newton's law of gravitation, F equals G m1 m2 over r square. Understand the concept of gravitational field strength. Derive and use the equation small g equals big Gm over r square for a gravitational field. Derive a relation between small g and big G and determine the mass of the Earth and its mean density, and understand the variation of small g with respect to r. Click the play button and consider two bodies of masses m1 and m2 separated by a distance r. According to Newton's law of gravitation, the force of attraction between the two objects is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. F is proportional to negative m1 m2 over r square. F equals negative g times m1 m2 over r square, where g is the universal gravitational constant, which equals 6.67 times 10 to the power negative 11 Newton meters square per kilogram square. The negative sign denotes that gravitational force F is a force of attraction.
Okay, so let's look at here. According to Newton's law of gravitation, Newton's law related to the force. That means that Newton's law of gravitation, that means involved in the gravity, force of the gravity. So from here, Newton's law of gravitation states that the force between 2-point masses, okay, no matter where is it, either in the Earth or outside the Earth, in the space or everywhere, as long as two objects with mass is directly proportional to the product of masses. That means that m1 times m2, and inversely proportional to the square of the distance, inversely divided by r squared, when it's become a formula, and from a formula F equal to negative g. G is a constant, where G is the universal gravitational constant. The value of G is 6.67 times 10 to the power negative 11 Newton meter square per kg square. So this formula shows that it's negative. What is meant by the negative? The sign of the negative. The negative represent the force is the attractive force. That means that m1 and m2. Between them, the F is in opposite direction. Okay, so opposite direction among them. Okay, so this will be the negative. We use the negative sign. Something is pulled and move in opposite or move towards the big object.
F equals G times m1 m2 over r square denotes the magnitude of gravitational force of attraction.
So from here, normally we apply, if we just want to find the magnitude of the force, That means that F is equal to G m1 m2 over R squared. Negative not means that it is negative value or less than 0, but negative show that that is the attractive force between the two objects. So what is meant by gravitational force? That is the attractive force between all bodies that have masses, not only in Earth, but also outside the Earth and also the space or universal.
If the gravitational force is a force of attraction, why shouldn't two students sitting 0.50 meter apart be attracted towards each other?
So from here, if the gravitational force is a force of attraction, why shouldn't two students? The two students never did or do not experience any attractive force. So actually the concept like that. When we sit in a room, that means in classroom, or anybody beside you, no matter how much is the distance. Let's say the distance is very near. Somebody just sit side by side with you, but both of you never experience any attractive force. Why? According to the concept, according to the Newton's law of gravitation, any two objects with masses will experience an attractive force.
Let the masses of the two students be 40 kilograms each. Applying Newton's law of gravitation, the force of attraction between them can be calculated as shown. Force of attraction F equals G times m1 m2 over R square. When m1 equals m2, which equals 40 kilograms, R equals 0.50 meter. F equals 6.67 times 10 to the power negative 11 times 40 over 0.50 square. Thus, the force of attraction between the two students
equals 4.27 times 10 to the power negative 7 Newton.
So from here, actually, both of them experience an attractive force. The magnitude of the force is 4.27 times 10 to the power negative 7 Newton. Negative 10 to the power negative 7 Newton means that the force is very, very, very small. Why? Because the G is 6 point, the constant of G is times 10 to the power negative 11. And cause the force, actually the force between them, there is an attractive force, but the force is very, very weak. So until we can't experience it.
The force of attraction F between the two students, 4.27 times 10 to the power negative 7 Newton, is negligible. Nevertheless, the gravitational force of attraction F exists between any two objects in the universe. Click View to view the labels of the apparatus used by Cavendish to verify Newton's law of gravitation.
Okay, so this one, okay, is an experiment, an apparatus to verify the Newton's law of gravitation. But this one, okay, is not in our syllabus, but as an extra knowledge, we can see how they use the apparatus, how the scientists use the apparatus to verify the Newton's law of gravitation. As we know that in our, when we are in primary school, teachers told us gravitational force is explored by Newton's, right? Isaac Newton, Sir Isaac Newton. Where, how? That means that when Sir Isaac Newton slept under the apple tree, and the apple fall and hit Newton's had. So is it that one, the experiment? No. Actually, okay, scientists use this apparatus to verify the Newton's law of gravitation. So this is not in our syllabus, but just for extra knowledge. So this is the part of the experiment apparatus.
The deflection theta of the torsion rod connecting the two small masses is directly proportional to the gravitational force of attraction F between the smaller mass and the larger mass. Cavendish used different pairs of spheres of different masses. Click Experiment 1 and observe the angle of deflection theta of the torsion bar for a particular pair of spheres.
So this object with a very, very small mass. Okay, actually the mass is as light as the polystring. When the two objects deflect each other, that means that the angle is taken.
Click Experiment 2 and observe the difference in the angle of deflection theta of the torsion bar when the masses used are bigger.
So that means that they use different mass and get the angle.
Click Compare to compare the angle of deflection theta in the two experiments. The angle of deflection theta is larger when the masses are increased.
So that means difference object, difference angle. The greater the object, the greater the mass of the object, the greater the angle of deflection. Why? Because the object, let's say the black object with the big black object with the small one, they will have the repulsion force. So the repulsion force, the force between them, the magnitude same with the attractive, but the force between them cause they repel each other. So this means that we get the angle of deflection.
Thus, the gravitational force between two bodies increases when the masses are increased. To study the variation of the gravitational force F with distance of separation between the masses, Cavendish used the same pairs of spheres, but changed the distance of separation. Click Experiment 1 and observe the angle of deflection theta of the torsion bar for a particular distance of separation.
So the angle is taken.
Click Experiment 2 and observe the difference in the angle of deflection theta of the torsion bar when the distance between the masses is increased.
Same object, but distance between the two objects increase. Then get the angle.
Click Compare to compare the angle of deflection theta in the two experiments. The angle of deflection theta is smaller when the distance between the masses is increased. Thus, the gravitational force between two bodies decreases when the distance between the masses is increased.
So what we can conclude that the formula of F equal to G m1 m2 over r squared is actually come from this experiment. This experiment proves that the force between the two objects is directly proportional to the product of m1 and m2. That means m1 times m2, and inversely proportional to the square of their distance separation.
Conclusion: F is directly proportional to m1 times m2, and F is inversely proportional to r square. On combining these two results, we get F is proportional to m1 m2 over r square. Hence, F equals G times m1 m2 over r square.
This is how the scientists derive and prove the formula.
Summary: according to Newton's law of gravitation, gravitational force of attraction between two masses m1 and m2 is directly proportional to the product of the masses. F is directly proportional to m1 times m2. Gravitational force of attraction is inversely proportional to the square of the distance between the two masses. F is inversely proportional to r square. Therefore, the force of attraction F between two masses is proportional to m1 m2 over r square. Thus, F equals g times m1 m2 over r square. Click the play button to observe the motion of a spaceship towards the moon. Click at any of the points marked along the path of the spaceship to observe the gravitational force F1 of the Earth on the spaceship and F2, the gravitational force of the Moon on the spaceship. Compare the magnitude of F1 and F2. Keep on clicking along the path of the spaceship until F1 equals F2.
At this point, F1 is the force, attractive force between the spaceship by the attracted by the Earth. F2 is the force, attractive force on the spaceship by the moon. Okay, so the size of the arrow, the length of the arrow show the magnitude of the force that act on the spaceship. Now, when the object is nearer to the at first point, we found that the attractive force by the Earth is greater than the attractive force by the moon. How about the second dot? The magnitude of F2 increased, but F1 reduced a bit, right? Okay. At third point, is there any difference F1 and F2? Yes, F1 slightly greater than F2. And next, is it equilibrium? Okay, almost, but actually F2 is a slightly shorter than F1. At this point, yes, F1 is equal than F2. Okay, that means that the attractive force by the Earth and the attractive force by the moon is equal. Okay, ladies and gentlemen, why the force at this point F1 equal to F2, but the magnitude of the force from a left and right are equal, right? But the distance between the spaceship and the Earth is much greater than the distance between the spaceship and the moon. Why?
In the picture, we see that the magnitude of both the forces F1 and F2 are equal when the spaceship is at a particular distance x from the Earth. What is the value of x? F1 equals F2. G, small m, big M1 over x square equals G, small m, big M2 over 3.8 times 10 to the power 8 minus x, the whole thing square, where small m is the mass of spaceship, m1 is the mass of the Earth, which equals 6.0 times 10 to the power 24 kilograms. m2 is the mass of moon, which equals 7.4 times 10 to the power 22 kilograms. G equals 6.67 times 10 to the power -11 Newton meter square per kilogram square. X is the distance between the Earth and the spaceship. On rearranging, we get x square over 3.8 times 10 to the power 8 minus x to the whole thing square equals m1 over m2. Substituting the known values, we get x squared over 3.8 times 10 to the power 8 minus x to the whole thing square equals 6.0 times 10 to the power 24 over 7.4 times 10 to the power 22, which implies x over 3.8 times 10 to the power 8 minus x equals 9, which gives x equals 3.42 times 10 to the power 8 meters. Thus, the distance x of the spaceship from the Earth equals 3.42 times 10 to the power 8 meters.
Okay, let's look at the example. Consider this is the Earth. And this is the Moon. The distance between the Earth and the Moon, okay, is equal to, okay, so the dimension, yeah, okay, let's say this distance, okay, and the spaceship is at the middle, along the path, okay, any point in between the Earth and the Moon. Let's say the distance of the spaceship from the Earth is distance of x, okay, and given that the distance between, this is a constant, yeah, because the Earth distance and the Moon distance will be equal to how much? 3.8 times 10 the power 8 meter. Okay, so what is the distance between the spaceship and the Moon? That means that for this, it will be 3.8 times 10 the power 8 minus x. So this will be the distance. So that's why the distance between the, okay, distance between the spaceship and the Moon is 3.8 times 10 to the power 8 minus x. Okay, so the mass of the Earth, this is a constant, never change. The mass of the Moon, this will be the constant, and g is a constant, and this x is constant. Normally in exam, all this value will given to us. Okay, so is the distance will be given in the test. Okay, don't worry. Yes, the distance, everything will be given. Okay, so now, ladies and gentlemen, you know or not, for the new KSSM, okay, so if you have a brother or sister, okay, starting last year, okay, Form 4 starting last year, so this means that they already learned this part. This will be one of the chapter in Form 4. So, ladies and gentlemen, let's move on. Let me clean the.
If F1 is the gravitational attraction of the Earth on the spaceship and F2 is the gravitational attraction of the Moon on the spaceship, where is the spaceship when F2 is greater than F1?
F2 greater than F1 will be here. Okay, so this means that when the spaceship near to the near to the Moon, the attractive force between the Moon and the spaceship will be greater.
When the spaceship is at a distance greater than 3.42 times 10 to the power 8 meters from the Earth, the force F2 is greater than the force F1.
This means that 3.42 times 10 to the power 8 meter is the distance where the force are equal, right? Okay. So this means that when it is nearer, greater than that, greater than the distance, this means that the F2 will greater than F1.
Summary. The gravitational field strength G at a point in a gravitational field is defined as the gravitational force of attraction per unit mass at that point. G equals gravitational force over mass, which equals F over m. The unit for G is Newton per kilogram, which equals meter per second square.
So this means that now the G will be the gravitational force per mass, right? Where we learned before gravitational force, F equal to mg. Correct? All the G will be equal to F over m. What is this? Actually, this we learned in the Form 4 syllabus before. Gravitational field strength is the force per unit mass on the body in a gravitational field. Let's look at the let's look at, let's say this is the Earth. There will be a region like that. Okay, so if any object put inside the region, that means it will fall to the, it will attract to the surface of the Earth, it will fall down. If any object at any distance still within the area under the inside the dot line, dot circle, that means it will fall down. If outside, that means it will not fall down anymore. So we call that this, what is this? This is a region where we call that is the gravitational field. What is meant by gravitational field? That is a region where an object experience gravitational force or gravitational pull. Okay, and then let's say the Earth can pull an object, any object inside the gravitational field, right? So let's say you are 50 kg or 60 kg. The Earth pull an object with 60 kg. Okay, consider two conditions. Another one, we have a big building. The big building, consider with, okay, how many billion kg, for example, a tall building. So how the Earth know that how much of the force needed? If the Earth provide the force, okay, that attract the big and tall building on you, okay, if the Earth attract you with the same force that attracted to the big building, what happened? You will never move anymore, cannot move already, because the attractive is very, very big on you. We can move, we can jump, we can move, because our body can against the gravity. For example, for certain gravity. So from here, how strong is it? How strong is the gravitational field? Okay, the strength is, okay, every 1 kg of object Earth's pull with 9.81 Newton. Okay, so this means that this is the G. What is the G? You see, Newton. Okay, every 1 kg, Earth pull with 9.81 Newton. That means that the G will be equal 9.81 Newton per kg, right? Every 1 kg, the Earth will pull with 9.81 Newton. So this shows that how strong is the gravitational field, G. Ladies and gentlemen, as we learned before, G can be 9.81 ms-2, right? And G also equal to 9.81 Newton per kg. Both of them with the same dimension. Both of them with the same unit actually. So Newton per kg actually will be, for example, I do it here, yeah, kg ms-2 times with, okay, Newton, okay, per kg times with divide by kg. So at the end, you see, we get ms-2. So Newton per kg actually same unit with ms-2. If G equal to 9.81 ms-2, this G represent the gravitational acceleration. If the G is equal to 9.81 Newton per kg, that means that this G represent the gravitational field strength. Gravitational field strength means that how strong is the gravitational field. How strong, how much of the force, okay, how much of the force the Earth provided. So for every 1 kg, the Earth will attract with 9.81 Newton. That's all. Okay, let's move on.
Summary. The gravitational force of attraction between the Earth and the spaceship is equal to the gravitational force of attraction between the Moon and the spaceship at a distance of 3.42 times 10 to the power 8 meters from the Earth. The gravitational field strength G at a point in a gravitational field is defined as the gravitational force of attraction per unit mass at that point. G equals gravitational force over mass, which equals F over m.
So this means that G have two, yeah, remember, yeah. One is the gravitational acceleration. G also represent the strength of the gravitational field.